I want to explain today how diesel combustion works. It doesn't work much like gasoline engines at all, except that the pressure pushes a piston down. Everything else is a lot different, but they still work on the same four-stroke cycle. Diesel engines have no throttle plate, no carburetor, no way to regulate the air going into the engine when the engine is running through the intake manifold. The intake manifold is open except for an air cleaner, so they get full air coming in all the time while they're running or trying to start. And their exhaust system works just like any conventional exhaust system on any engine. Diesels cannot work with a carburetor. The reason being, diesel fuel is an oil. Gasoline is like a solvent. It wants to turn to vapors, and diesel does not want to turn to a vapor unless you heat it to a very high temperature. But if you do, it wants to ignite because it ignites at a much lower temperature than gasoline. All diesel engines are fuel injected. There's two different kinds. One is mechanical fuel injection, and one is common rail fuel injection, or CRD, common rail direct injection. Well, common rail is the best because it has electronically controlled electronic fuel injectors. They're called piezoelectric injectors, and these are high-frequency injectors, and they can shut off and on the fuel coming out of the injector nozzle in little pulses. The fuel comes out in all injector nozzles like a V-shaped spray, a conical V-shaped spray, to aerosolize it to turn it into a mist. Well, with common rail diesels, it shuts it off and on very quickly in pulses so that it doesn't have that loud crack when it all comes out at one time, like the crack a diesel noise, like the crack a diesel engine makes when you typically hear an older one running. That has a second mechanical advantage, which I'll show you in a moment. Here is a typical gas engine, small air-cooled lawnmower block. Well, it really doesn't make any difference for this demonstration whether it's a gas engine block or a diesel block. That part of the bottom of the engine is exactly the same. So now the piston's at top dead center, meaning at the top of the cylinder, and typically that's where engines fire. Well, they usually fire just a few degrees or a little bit before they get to top dead center because fuel takes time to burn. And if you fire it too late, the fuel's not all burnt by the time the piston gets down to the bottom. Well, diesels don't have spark plugs. They light the fuel by compressing the air to a much higher pressure than in a gasoline engine called the compression ratio. When you compress the air in a gasoline engine, the average pressure in the cylinder before it fires is up to 120 psi in normal engines. Much more in race engines and high-performance engines. But in a diesel, the compression ratio, instead of in a normal gasoline engine at 9:1, the compression ratio is a minimum of 17.5:1, so your cylinder pressures are very much higher, over 500 psi. When you compress air, it gets much warmer. That's how diesel is ignited. So just like a gas engine, when the piston's just around the top at TDC, the injector turns on and fires the fuel in there, and it's already hot enough in there that it will ignite the fuel, and that pushes the piston down. When a cold diesel engine is not spinning around that fast like when you're trying to start it, it doesn't quite very easily make enough temperature in the cylinder by compressing the air to light the fuel. So we have what's called a glow plug. Well, here's a spark plug. I'm just showing two to compare size. There's not a lot of difference in size. Glow plugs can have a longer tip. The tip is the business end. Inside there is a resistive metal that gets hot when electricity is applied. Positive power is applied to the post in the top, and negative is through the ground around the threads. This little shaft sits in the combustion chamber of a diesel engine and gets to about 600 or 700 degrees Fahrenheit, and that's certainly hot enough to ignite the fuel because part of the injection spray actually hits the glow plug. On some engines, the glow plugs cycle off and on a little bit while the engine's still cold, just to help make them start firing better and more evenly while the engine's cold. But in most vehicles, the glow plugs completely shut off as soon as the car is started. These things are like a light bulb. They either work or they don't work. They just don't halfway work. So they do burn out. They're easy to test. You just have to unhook the wire that goes to them, put one end of your meter to ground on the engine block, and the other one set on to the input post. They should always read less than an ohm of resistance. Here is the cylinder head of an old 1.6 not direct injected diesel Volkswagen engine. Of course, the head's upside down. You can see the intake valve, the exhaust valve, and where the combustion chamber is. Now this head is the flathead model design because diesels want a smaller combustion chamber to increase the compression ratio, so the cylinder head is flat. In gasoline engines it's cupped out. There's 4 little holes along the head, and that's where your glow plugs screw into. Now this is the old-fashioned design, which has a pre-chamber. It's that little chamber here. There's the injector. There's threads on here where the fuel goes in. There's little bleeder tubes. Those are for purging and for excess fuel. So if your engine runs out of fuel, it's easier to get it restarted. And of course, when it's running, the excess fuel just goes back to the tank. So what happens is you prepare to start your motor, the glow plugs warm up. That little hot tip is inside that little pocket, which actually runs through the head like that. The injector is at the top of that finger-shaped pocket. When you go to start the car, get out of here, kitty. It shoots a mist of fuel onto the tip of this hot glow plug, and then the mist comes out there firing and pushes the piston down. This by far is not the best method to make a diesel engine. Direct injection is much better, and direct injection is when the injector is either in between the valves or someplace in the middle of the head near the valves, squirting the fuel directly towards the piston. And then if there is a glow plug in this type of engine, the glow plug is still coming out in a position where it can hit some fuel and ignite it when it's cold. Direct injection engines have more torque, more horsepower, and I kind of think they start easier too. But they're a little bit more complicated to make a head with that design. Since this head is not the common rail design, it has 4 separate injectors fed by 4 separate input tubes, and the input tubes go to a combination high pressure injector pump and fuel distribution mechanism. So when the pump is mounted here, it's being turned by the timing belt, it's pressurizing the fuel, and on the back side of it here, it looks something like the distributor cap of a car, except all the parts are metal, and it distributes the fuel on time to each cylinder when it's ready to fire. If this were a common rail design, it would have a fuel rail that attaches to each injector. There wouldn't be these little bleeding tubes or purging tubes, and each injector would have a connector, electrical connector to it with 2 pins where the computer would send a signal to it to pulse the fuel in. And that would be powered by most likely a high-powered injector pump to put the pressure in the fuel rail, and the pressure in the fuel rail would exceed 2,000 psi. The reason why you'd want that much pressure in the fuel rail in a diesel is so that the pressure in the injector can exceed the pressure that's in the firing chamber of the engine, so that it can still come out at a powerful mist, and the higher the pressure is too, the more finer the mist it can be, and the lower the fuel consumption. Now back to the disassembled engine so that I can show you a mechanical disadvantage that internal combustion engines have. All engines fire around top dead center when the piston's at the top. That's when there's the maximum cylinder pressure to push that piston down. Now I'll show you why that's a disadvantage. Rotate this back up to the top. Piston's at the top. When the piston's at the top, and you have the maximum cylinder pressure, whether it's firing because it's a diesel or a gasoline engine, there's no mechanical energy being transferred to the crankshaft to rotate it. I'll show you in this picture. So if there's the combustion chamber, and that line would be TDC, and the piston was at the top, the arm of the crankshaft would also be at the top, and the rod would be vertical. So that means when you have maximum pressure there, it's pushing everything straight down towards the crankshaft, but not rotating anything. So that maximum amount of energy is not even actually being used at that moment in time. It's not till the crankshaft rotates 45 degrees that the conversion of pressure force to mechanical energy and twisting force is actually starting to become efficient. And it's only efficient during about 90 degrees of the stroke. And then once the crankshaft gets almost vertical again at DDC, bottom dead center,
it has no more mechanical energy coming from the piston to rotate the crankshaft again. Kitty! So even though the power stroke is 180 degrees from here all the way to here, only about 45 degrees of it is doing much mechanical work for the engine to help twist that crankshaft efficiently. If there was a way to design an engine that would have maximum cylinder pressure at 45 degrees past top dead center and use the effective power stroke at the 90-degree points here, then you would have a much more higher torque output engine, lower fuel consumption, and be transferring much more mechanical energy into turning that crankshaft. With a common rail diesel, it kind of uses its electronic advantage that controls when and how often the fuel fires through the injector into the burning stroke of the engine by first firing it when it's at TDC, when there's maximum pressure, so that it ignites, but not dumping it all in there at the same time like in a gasoline engine or in an old-fashioned diesel engine. Instead, it keeps sending little pulses of fuel out as the piston is going down, so when it's in this sweet area where it's making the most mechanical energy, it's still giving some more fuel to be burnt, and that's giving you better fuel economy, more horsepower, and more torque. You can't do this with mechanical injected engines at the pulsing rate that can be done with CRD.
And definitely having the fuel not all ignite all at the same time definitely makes a quieter engine. Now, many auto companies right now are also working on direct injected gasoline engines too. They still fire with a spark plug, but they can fire with much higher compression because there isn't already fuel in the cylinder that will pre-ignite before the piston gets to the top and cause pre-ignition and try to push the piston back down the other way, which gives you poor fuel economy, poor performance, and can damage pistons. So when a gasoline engine has more compression, that's more free horsepower you can get with no disadvantage to the engine whatsoever, no negative side effects except maybe nitrous oxide emissions.
So direct injected gasoline engines, which of course have to be electronically fuel injected, are the new thing of the future. You'll get better torque, better fuel economy, better horsepower, and better emission controls. I'll use this Volkswagen diesel head only as an example to show how current multi-port fuel injected gasoline engines are working. These are exhaust ports, these are intake ports. In the multi-port fuel injected engine, there's a raised bump here, and the fuel injector is here with its point sticking into the intake manifold, and it sprays its fuel on an angle towards the intake valve, so some of it hits the intake valve and reliquefies, which is not good because you prefer to be atomized, so it's a mist. Then the air rushing in at the same time just sucks that vaporized fuel and mystified fuel into the combustion chamber. If it were direct injected gasoline engine, someplace more vertical on the head, maybe up here or something like that, or pointing here in a steeper angle, would be the injector spraying inside the cylinder area. That's much better. It's just more expensive to build and higher technology.
The two biggest differences between diesel fuel and gasoline are the diesel fuel is an oil and gasoline is more like a solvent. The second biggest difference is diesel fuel is fractionated and designed to light at a low temperature. It lights normally at less than 500 degrees Fahrenheit. Gasoline is the opposite. It's designed to light at the highest temperature possible so that you can have more compression in the engine, which gives you more energy and more free horsepower. So gasoline typically lights at 700 degrees Fahrenheit or more. We call this the octane rating. The higher the octane rating, say for example from 89 to 110, like for airplane fuel, the higher the number, the higher the temperature which the fuel ignites. And that means since there's already fuel in the cylinder when a gasoline engine is running, you have to have some way to prevent it from igniting until it's the right time and a spark plug does it for it. On a diesel engine, if you had the fuel somehow vaporized or atomized while the engine was compressing, like in a typical gasoline engine, it would most likely fire when the engine was warm before the piston got to the top and push it back down the wrong way. So like the way spark timing works in an engine, diesel injector timing works that way. It fires the fuel when the engine's at around TDC, so that the piston being moved around by the flywheel's momentum pushes the piston down in the right direction when it ignites automatically just by the extreme temperatures in there. And finally, if you have a diesel engine and you want to run it on alternative fuels like heating oil, animal fats, cooking oil, vegetable oil, whatever, it doesn't matter. Your engine needs no modifications. You just have to make sure the fuel is properly filtered, that if it's a high glycerin type fuel, that you have a method of getting the glycerin out of the fuel, because that's bad for the engine and bad for the injector pump. And if it's a fuel that gels easily, well, you have to make sure that you have a solvent in it so it doesn't gel easy in cool weather. And of course, any type of non-diesel type fuel or non-heating oil type fuel, especially vegetable derivative ones, definitely have a problem with gelling and thickening up in the wintertime and become unusable in cold weather.